There we go. Hello and welcome back to Calculus 1 section 3.11 on related rates. Word problems. Lock the doors. No one is leaving, right? This is one of the, in my opinion, most important and valuable sections because it's application of mathematics, and most of you here are applying mathematics, whether it be business, economics, engineering, right? So we are first going to take a look at the title and understand the title. So first of all, we have the word rates, and when you see word rates in calculus, you immediately think the derivative, because derivative as a rate of change, right? So we are going to be relating derivatives. It's plural, right? Rates. So you have to have at least two different derivatives per formula to create related rates. So the idea is to, again, measure the change. And it's a very powerful section because it measures the way the things evolve in time. So pretty much all of the derivatives we're going to deal with are going to be taken in respect to time because things evolve and change with time. We mentioned a few times in the class already that, you know, in the morning when you wake up, you are the tallest and lightest for the day in terms of like height and weight. So your body worked out all of the food you put in, right? Because you were unconscious for like 8 hours. And also you were horizontal, unless you sleep propped up to a tree or something. You were horizontal to for 8 hours, so your joints stretch and everything. So you're the tallest. As soon as you wake up, you're the tallest and lightest for the day. Now that starts changing as you are eating. Obviously, you're increasing the body weight, and as you are walking around, your body weight is pushing down on joints. So you are also getting shorter. Now these are all, you know, fractions of a fraction of an inch. So you don't actually see these. Well, weight goes up in pounds and goes down in pounds, but the height you can't really detect very well. And any other system would have the same effect. If you take an ice cube and you put that in a hot coffee, right, to make the iced coffee, it's going to start melting, and it's going to melt from all sides. So when you are thinking about the melting ice cube, which I hope all of you can relate and think of, that ice cube is getting smaller, which means it's going to have less volume and it's going to have less surface area, and each one of the sides is going to be shorter. Also, the diagonal of the cube is going to get shorter, and the diagonal of each of the sides of the faces, right, is also going to get smaller. So collectively, the whole system is getting smaller with all of its qualities that explain and describe that cube. Everything is going to become smaller. And the beautiful thing about calculus is calculus can relate all of those, and you can, if you know some of the information, you can calculate all of the information of how fast it is getting smaller. So I hope you would understand that if you have a drink that it's already cold, and then you have a room temperature one, and you have the hot one, like coffee, just brewed, right? And then you have, let's say, magma in your volcano. Right? If you take a single ice cube and you toss into all of these 4 different temperatures, the ice cube is going to behave differently, right? It's going to melt in all of these environments. Even in a chilled drink you take from the fridge, when you dump an ice cube in it, it's going to melt. It's just going to melt very slowly, right? Because think about it, right? if the temperature of the ice cube and the temperature of the drink out of the refrigerator were the same, your drink would be frozen, right? Because it's just 99.99% water, and then you have whatever amount of whatever defines that drink, right? So if your drink is not frozen, that means that if you toss the, I don't care what temperature it is, if it's not frozen when you throw in ice cube will melt. Just give it time. So now we can observe the ice cube losing volume, losing surface area, and all the other aspects of it in time. But we want to know how fast is that happening. Now, clearly, we'll see engineering applications to this and others. In the beginning, we want to understand the mathematics of doing the problem. So let's talk about shrinking ice cube, right? Melting ice cube. But then we'll have other examples as well. So let's start with an ice cube. Ice cube has 6 sides. It's like your regular, dice, numbers 1 through 6 that you can toss around. So you have an ice cube with the side A. And now you need to figure out you want to figure out all of the aspects of this ice cube in terms of formulas, right? So you have side, and we're just going to call that A. And you have the volume, and that better be A cubed, because it's length times height times the width, right? So all 3 of these are A. You have the surface area, and the surface area S is going to be the area of each side, and then you add all the sides. So what's the area of one of the sides? Very good. A squared. And how many sides do you have? 6, right? So 6A squared for the surface area of this. Now that will be the part that you paint, right? So if you want to know how much paint you need to paint a cube, well, it's going to be each side, area of each side, and you add them all, so it's all A squared, so 6A squared. Diagonal of any of the face, right? Any of the sides. Lowercase d. So that's the diagonal on the face. You have let's say number 3 on a dice. So, right, regular dice. Look, number 3 looks like this. Well, that's technically connecting the diagonal. Okay, that's what I'm talking about. So diagonal of one of the sides, which is this lowercase d, is going to be a root 2. If you do the Pythagorean theorem, you have a squared plus a squared, square root of that. A squared plus a squared is 2a squared. When you take a square root of that, square and a root cancel, and you just have a root 2. And then you have the big diagonal, the one that connects opposite sides of the cube. So let's say these 2 sides, right, running right through the cube. So if this was a cube, the room we're in, we are going to connect the where the printer is over there in a corner, bottom of that room, to the ceiling end on the opposite side of the room. So diagonal will run through the space. That's the capital D. So this is the major diagonal, right? So you have diagonal of each side, and then you have the major diagonal. Now, major diagonal is a little bit trickier to compute because the major diagonal, as you can see, is using the diagonal of a side and the side of the die. So you have the square root of a root 2 squared plus a squared, and the capital D is 2, 3, so a root 3. angle here, a root 3. So the minor diagonal of each one. Now this is all because it's squares. As soon as you use the rectangle or something, all of these formulas obviously change. But these are all of the formulas that exist regarding the cube. And this should be the easiest of all to work with. You have a side A, volume A cubed, surface area 6A squared, diagonal of each of the sides, a root 2, and the major diagonals inside are going to be a root 3. So these are the specs. Now, what do I want to know? I want to know how fast this involves in time. And the way to do that, let's pick any of the concepts, say surface area, right? If I pick area as an example, I will take the formula, which I know, and I will take the derivative of that formula in time. Now, yay, implicit differentiation. Woohoo, right? So we get to use the stuff we learned before. So I'm taking the derivative of the formula in respect to time because you have to wait for the ice cube to melt, right? So that's the time component of the whole thing. So now the derivative of s is 1, and then we also have ds dt. So what I have over here is ds dt is equal to 6 times 2a, and then I have dA dt, right? We have to put chain rule for both of these sides because we are taking the derivative in t, and none of our variables are t, right? If you add some variable of t, you take the derivative of that, then you don't have the chain. But now that all of these variables do not match, you have to follow with a chain on every single derivative you take. So now, clean this up, and we have ds dt is 12a dA dt. This is mathematical model. This is what we are after, right? Now, this formula over here is called related rates. That's what related rates is. You see two rates. Guys, these are rates of change, right? And they are in respect to time. So the one on the left it's one of those days when technology says nope. So this over here is change of surface area in time, and this one over here is change of length of the side in time. So that's what they mean. And you see they're related by this 12a. So I can measure change of a side. I can measure that, right? So if I am able to measure the change in the length of a side, then I can calculate change in volume, change in diagonal, change in surface area, change in major diagonal, and so on. So there's always something that you can measure, and then you can use the related rates formula to calculate the rest. And that's something that is, in my opinion, really cool. So now I can say that for an ice cube which has the side equal 1 inch, right? Each way. So it's inch by inch by inch ice cube. And it's melting. And side, so it's melting, and side decreases. So sine decreases at the rate of 0.09 inches per minute. I don't care. Whatever we put. So find the rate of change of volume, which is actually what we would be interested in. We're interested in volume if it's. But then since it's math, also we can do surface area. And let's do major diagonal. The capital D. Find the rate of change of volume, rate of change of surface area, rate of change of major diagonal. Well, let's start with surface area because we already know. So for surface area, we already know that ds dt is equal to 12a dA dt. Now, what do we know from the text? From the text, we know that a is equal to 1 inch, and we also know that dA dt is equal to negative 0.09. It's melting, it's decreasing, right? So let me put that in blood over here. So negative. Also, guys, there's something cool that we need to talk about. It's units. You know, there are courses in general chemistry and physics. Yeah, all of those are jokes if you know the dimensional analysis right there. So the units over there tell you that this is dA dt, because A, change in a side, well, that's your inches, and in time, that's minutes. So you see over here that the formula clearly states that this concept over here that it's given in a text is change in a side. Well, it says that the side decreases at the rate. So put all of these things together, right? You have a side, you have a rate, you know it's happening in time. So here you go, side, rate, and happenings in time. Do you see how the three concepts work together to give you that? And then I put minus on 0.09 because it's melting, it's decreasing. So I put the minus there. What's left for us to do? We'll just plug in, right? They're looking for the change in surface area. So that's 12 times 1 times negative 0.09. That's it. I hope you're not disappointed, because that's it. So now we have 12 times 0.9. It's going to be obviously negative. So we have negative 0.08. And now the units for this are inches squared per minute, because it's area, and area is squared. So we cut, and we see the minus, which means it decreases. And that makes sense, because if the side is decreasing, well, surface area better be decreasing with it. And it does. It's a minus there. How about volume? Well, volume is equal to a cubed. And then we hit this with the derivative. Good morning. We hit this with a derivative dt. And when you hit this with a derivative, you get dv dt, right? Derivative of v is 1, and then you have the chain rule, dv dt. On the other side, you have 3a squared times dA dt. Again, chain rule. On the other side, there is a chain rule. You still have the same info from before, that a is equal to 1 and dA dt is equal to negative 0.09. So now you plug that in to see the change in volume. That's 3 times 1 squared times negative 0.09. Well, that's negative 0.27 inches cubed per minute. So you see the negative over here, which means the volume is decreasing, and yeah, it makes sense. It should be decreasing. Ice cube is melting. And then we said major diagonal. Well, major diagonal was a root 3. Hit that with the derivative in time. Again, we are looking for changes in time, which is the reason why you are taking the time derivative. So we take the derivative in time, we get dd over dt is equal to just root 3 dA dt. Plug in, the change diagonal in time is root 3 times negative 0.09. Let's use abacus to calculate that. So square root of 3 times negative 0.09 is negative 0.156, whatever, inches per minute, because the diagonal is just length. It's one dimensional. So these are the things that we have, and this is the first problem which we did. So let's recap all of this stuff, and then we'll move to different geometry. So we are familiar with the concept of a cube, and then we are taking an example of an ice cube. An ice cube has a side A, which is one-dimensional length. It has the volume A cubed, which is the stuff inside. If you look at this classroom, the amount of air in this room is the volume of the room. Or you take a look at the bottle, how much water and liquid you have inside. Surface area is how much paint you need to just paint the outside. In the case of the cube, you are painting the ceiling and the floor and all 4 walls from the outside. And then diagonal. On each side, there is a diagonal, so there's 6 diagonals, in this case all the same, right? 6 diagonals. And then you have the major diagonal that connects 2 opposite corners, from the floor into the ceiling in the opposite corners. Now, what I'm going to do is I'm going to leave that ice cube in the liquid environment to melt, and it's going to melt equally from all sides. And as it melts, everything gets smaller together. The diagonals, the volume, the surface area, and obviously the length of the side. And we can use calculus, our related rates, to relate those changes together. So I did the full derivation over here for area. So you start with the geometry formula from your middle school. You take the time derivative, and now you have the change in time. So the change of surface area in time, one more time, to the finger, see the finger? The change in surface area in time is equal to 12a of the change in length of the side in time. Learn the words. translate this mathematical language into regular English, because that's what it is. Change of surface area in time is equal to 12A times change of length of the side in time. And once you decipher that, the rest is just plugging the numbers in. The book starts off with environmental problem. Like let's say BP is one of the leading companies in these things. So the oil spill, all right? No, I'm serious. All right. Are you all familiar with the problem of mixing wine and vinegar? You're not? Let me put that down for you. So, if you're mixing wine and vinegar, it goes like this. If you have 100 gallons of vinegar and you add a gallon of wine, you have vinegar, right? So you have 100 gallons of vinegar and you add 1 gallon of wine, you have vinegar. If you have 100 gallons of wine and you add 1 gallon of vinegar, you still have vinegar. So that's the mixing problem, all right? So now this is the same thing with oil and water. Just a tiny speck of oil can contaminate a lot of water. Water is very fragile. The battle for the environment is not a battle for planet Earth. If anyone tells you that, you immediately know there's something cognitively wrong with that person. Save the planet? Yeah, please. All right, it's a rock, all right, that goes around the sun, and a long time when we are dead as a species, it will still go around the sun, all right? And we're insignificant in that matter. When someone is talking about the environment, we need to be honest. It's the environment in which we live and we can survive. Polluted waters are just fine for the whole planet because all of those pollutants came from this earth, all right? So you throwing around plastic bags everywhere and dumping stuff in the water, really, planet doesn't care, because it's not that we are importing that stuff from a different planet and all of a sudden the planet is going to go crazy. No, it won't. Like, that's just old stuff, right? There's a notion that the only reason planet needed us to evolve is to just make up plastics because nature wasn't able to. I know, right? So, environmental issue. Yeah, forget about the big idea of saving the planet and just focus on saving the environment so you can survive, actually, right? So when you put something really bad in the water, you do two things. First of all, you're making that water poisonous for you to drink, and then you kill the fish so you can't eat right? You can't eat that either. So there you go. It's a very simple argument. We don't need anything extra to what the truth actually is. So when you are drilling for oil, which will hopefully stop because electric cars are coming up, when you introduce some of that oil to the water, it spreads. And then if we don't clean it, it's just going to stay there. All right? So what we are going